Hello everyone, welcome to session 10. And today we actually want to discuss about the propulsion in aeronautical engineering. So what is propulsion actually? The word propulsion is derived from two Latin words, pro, which means before or forward or prior, and pellere or pellere, which means to derive. So propulsion means to push forward or to derive an object forward. So a propulsion system is a machine that produces thrust to push an object forward. We know that on airplanes, thrust is usually generated through some application of Newton's third law of action and reaction. Here we have a gas or some working fluid which is accelerated by the engine, and the reaction to this acceleration produces a force on the engine. So if we want to look at the history of propulsion, it goes back to 250 BC. It's the hero's engine or Aeolipile. You can see it in here. And the hero of Alexandria described this device in the Roman Egypt. And this was actually the first recorded steam engine or reaction steam turbine in the time. After Leonardo da Vinci in 1500s about the paddle wheel, you see a drawing of the paddle wheel in here, which is driven by ascending hot air to rotate a barbecue speed. Actually, we had another improvement in the propulsion. And the idea of axial flow impulse turbines came from Italian engineer back in 1629, Giovanni Branca, who designed the turbine wheel, which is driven by a steam jet. You can see he had the idea of boiling water, make it steam, and then the steam will hit the blade of this turbine when it is rotating. So this is the first known evidence of an axial flow impulse turbine. Back in 1687, the English philosopher and mathematician Sir Isaac Newton formulated 3 laws of motion, and this formed the basis of modern turbomachinery. And it says, actually we all know that a body remains either at rest or in motion of constant velocity unless there is an external force acting on the body. The second says the sum or summation of forces acting on a body equals the product of the body's mass times the acceleration produced by these forces, or the well-known formula F is equal to ma. And the third law says that for every force acting on a body, the body exerts a force of equal magnitude and opposite direction along the same line of action as the original force. So in this slide, we're going to look at a video that I have taken from YouTube about the jet propulsion. So let's watch it together.
Jet propulsion can be defined as the force which is generated in the opposite direction to that of a discharge of fluid under pressure escaping through an opening. The force that makes a lawn sprinkler, similar to the one shown here, rotate when water flows through it is one example of jet propulsion that is readily apparent in everyday life. And the thrust that sends rockets, like this one, into space is another, which is perhaps not such an everyday occurrence. Whatever the form that the device utilizing jet propulsion takes, it is essentially a reaction engine, which operates on the principle of the third law of motion, as stated by the English physicist Sir Isaac Newton in 1687, which is that every action has an equal and opposite reaction. The first recorded use of a reaction engine was by Hero of Alexandria in 250 BC. Hero's engine, a representation of which is shown here, consisted of a sphere into which steam was introduced under pressure. The steam was fed through apertures in the centre of the bearings upon which the sphere was allowed to rotate. Allowing the steam to escape through nozzles in two bent tubes mounted opposite one another on the surface of the sphere created thrust, which caused the sphere to rotate around its axis. It's alleged that Hero invented his engine while he was investigating different methods of opening the doors of a temple in Alexandria. In recent times, one of the first attempts at creating jet-powered aircraft resulted in the development of a hybrid design. An Italian, Secondo Campini, designed a system whereby an external power source, in this case a conventional piston engine, powered a compressor. The output of the compressor was mixed with fuel, the mixture of air and fuel ignited, and jet thrust resulted. Campini collaborated with the Italian aircraft manufacturers Caproni, and in August of 1940 the Campini-Caproni CC-2 flew. Although the Italians were unaware of it, a year earlier than this the Germans had flown their version of a jet aircraft, the Heinkel 178. This aircraft was powered by an engine designed by a young German scientist called Hans von Ohain. Despite the relatively sparkling performance for that era, it could travel at speeds in excess of 400 miles per hour, the German Air Force initially paid it scant regard, and it was never produced in any quantity. On the 8th of April 1941, the first official flight of the Gloucester E-2839 aircraft took place at Brockworth in Gloucestershire. Sir Frank Whittle had submitted patents for his jet engine in 1930, but it was not until 1939 that sufficient financial and technical backing was found to enable him to manufacture a flyable version of his engine. The firm of Rover had, reluctantly, initially been contracted to produce the Whittle engine, but Rolls-Royce, who could see its potential, eventually took over development of the engine, one of which is shown here. Rolls-Royce reworked the Whittle design to produce the Derwent engine, an example of which is depicted here. This engine was capable, in its Mark IV version, of producing 2,450 pounds of thrust. Later versions of the engine, capable of 3,600 pounds of thrust, were used to power the Gloucester Meteor F8, like the one shown here, flying at an open day at Royal Air Force Kemble in the year 2000. During a visit to the United States in early 1944, the leader of the Rolls-Royce design team found that General Electric were developing engines capable of producing up to 4,000 pounds of thrust. As a response to this, after his return, he initiated a project which culminated in the Nene engine, which at the time was the most powerful engine in the world, with 5,000 pounds of thrust. Possibly one of the most important but least publicized uses of this engine was its incorporation into the Russian MiG-15 aircraft, which was so effective in the Korean conflict. One critical difference between the German engines used in the Heinkel and the later Messerschmitt 262 and those developed from Sir Frank Whittle's original engine was the type of compressor employed. While the Whittle engine used a centrifugal compressor, similar to the example shown here, the German engines, like the BMW 003 model used in the Heinkel 162, utilized an axial flow compressor, similar in design to the cutaway model shown. Axial flow compressors have several advantages over the centrifugal compressor. For instance, whereas the centrifugal compressor compression ratio is limited to approximately 12:1, when the maximum of 2 stages are used in series, by adding more stages to an axial flow compressor, compression ratios as great as 40:1 can be obtained. The term compression ratio refers to the ratio of the pressure at the outlet of a compressor to that at its inlet. A second advantage of the axial flow compressor, almost as important as the first, is that the mass flow which can be obtained through an axial flow compressor is potentially much greater than the mass flow which can be achieved through a centrifugal compressor. As a consequence of these factors, the development of the early centrifugal compressor engines was subjugated in favor of the advancement of the axial flow compressor engines, which continues today. The principle of the gas turbine engine is basically the same as that of the piston engine propeller combination. They both propel a mass of air backwards. Mass times acceleration equals force. In a gas turbine engine, the mass, m, mentioned in the equation, is the air delivered by the compressor. The acceleration in the equation is the difference in the outlet velocity of the air, VO, to that of its inlet velocity, V1, due to the addition of heat energy. Force equals mass times V0 minus V1, which equals thrust. With the piston engine propeller combination, the propeller drives a relatively large mass of air backwards fairly slowly, while the gas turbine throws a small mass of air backwards relatively quickly. Newton's third law states, for every force acting on a body, there is an equal and opposite reaction. In the two cases quoted earlier, the piston engine propeller combination and the gas turbine engine, the force created by the mass of air being thrown backwards and its velocity generate a reaction in the opposite direction, driving the aircraft forwards. It must be remembered that the jet reaction does not result from the pressure of the jet on the atmosphere. In all instances, the resultant reaction or thrust exerted on the engine is proportional to the mass or weight of the air expelled by the engine and the velocity change imparted to it. The working cycle of the gas turbine engine is called the Brayton cycle, after George Brayton, an American mechanical engineer who invented the continuous ignition engine, which was the basis of the gas turbine engine. The Brayton cycle and the working cycle of the four-stroke piston engine, the Otto cycle, are very similar, as can be seen in this diagram. The induction, compression, power, and exhaust strokes of the Otto cycle are each matched by induction, compression, combustion, and exhaust stages in the Brayton cycle. One major difference, however, exists in that in the gas turbine engine, combustion, theoretically, occurs at a constant pressure, whereas in the piston engine it occurs, once again theoretically, at a constant volume. Power is developed in the turbine of the engine. Other differences between the piston engine and the gas turbine engine concern the continuous manner in which these processes occur in the gas turbine engine, as opposed to the intermittent procedure occurring in the piston engine. In the piston engine, only one of the strokes is utilized in producing power. The other three are effectively absorbing power, while in the gas turbine engine, the 3 idle strokes have been eliminated, thus allowing more time for the burning of fuel. This is just one of the reasons why the gas turbine engine has a greater power-weight ratio than the piston engine. The pressure-volume diagram shown here, otherwise known as the Brayton cycle, represents the working cycle of the gas turbine engine in its simplest form. Air at atmospheric pressure enters the engine at point A and is compressed along the line AB. Fuel is added in the combustion chambers, which is signified by point B, and the mixture is burnt, in theory at a constant pressure. In fact, the reduction in pressure shown between points B and C indicates that pressure losses do actually occur in the combustion chamber. The drop in pressure is created by the need to produce the swirl and turbulence necessary for efficient combustion, and this causes a pressure drop throughout the combustion chamber length of between 3 to 6%. Notwithstanding this drop, a considerable increase in the volume of the air is generated within the combustion chamber. Between points C and D, the gas generated through combustion expands in the turbine, where mechanical power is extracted from the energy in the gas stream, and the jet pipe, where the remainder of the gas stream energy provides a propulsive jet as it is discharged. In theory, the gas stream pressure attains a value equal to atmospheric pressure.
Okay, with this introduction, let's continue. We're going to discuss about the classification of propulsion systems. So, as I always say, actually within this course there is no need to know everything. I just need you to get familiarized with the terms and the names and stuff. So for today's session, it's also applicable to the terms and stuff in the propulsion system. So first of all, we can classify the propulsion systems into three main classes. The first one, which is the most extended one, is the air breathing or atmospheric dependent class. Then we have non-air breathing or rocket engines, the opposite side, and sometimes we can have some mixture or a hybrid engines or propulsion systems which can take air and use the air, and also they can just avoid the air and behave like rocket engines, so we call them hybrid or turbo rockets. So first of all, let's look at this left side, the air breathing or atmospheric dependent engines. What are these propulsion systems actually? These are the systems that actually rely on the air inside the atmosphere, or they are dependent on the air. So when there is no air, they cannot work. It means that outside the atmosphere, in the space, they cannot work. So we can classify them as jet engines, the propeller engines, as you see, and again a hybrid form of air of the propeller and jets. So the propeller ones are the oldest ones, and you can classify them as piston and turbo engines. And the piston engines, we all know what are they. The engines that are inside the cars are the piston engines. Also, we have engines inside in old aircrafts with piston engines. But a newer propeller type engines exist. We call them turbo engines. Actually, they are using a jet engine, but I mean the jet engine concept, but they are rotating a propeller. So as you see, there is a turboprop, there is a turbo shaft, and also there is a prop fan, or in other words, unducted fan. So these are all gas generators like jet engines, but the exhaust of the engine is not important to us, which what is important is the rotation of the shaft that is provided by the jet engine, and this rotation actually rotates the propeller, and this propeller actually makes the propulsion for us. On the other hand, as I said, we have the jet engines, and the jet engines are actually classified as turbojets, turbofans, and ramjets. So what are these? Turbojets, we will talk about the turbojets. These are the most, these are the simplest jets. The turbofans are actually the turbojets that another fan is connected to a turbojet, and we call it as a bypass concept. So we use some amount of air and redirect it through the fan. It wouldn't go inside the engine to be burnt with the fuel, but and we call this a bypass air, which is not burnt inside the engine. So it's just going through the fan. We will all of this in a moment. We will see all of these in a moment. And based on the magnitude of the bypass, we can have a low bypass turbofan or a high bypass turbofan. Low bypass turbofan means a turbofan that the amount of bypass air is low, and the high bypass turbofan is that the amount of the bypass is high, depending on the flow that is going inside the jet engine and will be burnt with the fuel. And the third classification is the ramjet. Ramjet is actually a jet engine that doesn't include any rotating components. As you saw in the video as well, there are some rotating components like compressor and turbine and fan inside the turbojet and turbofan engines, but in ramjet there is no actually a rotating part. So based on the combustion, we can have a subsonic combustion, we can have a supersonic combustion. So the one with subsonic combustion means a normal ramjet. The supersonic combustion ramjet is the scramjet, is called a scramjet, and also we can have a pulse jet. So we will see each of these one by one in a moment. And actually I said we have a hybrid thing. We call them the turbo ramjets. So if you look at the rocket engines or the engines which are atmospheric independent, you can classify them as chemical rockets and non-chemical rockets. The chemical rockets have been classified into more three classes: the liquid propellants, solid propellants, and also solid and liquid, so hybrid propellants. And the non-chemical ones, which are the ones that are not using chemical propellants. We do have the nuclear heated rockets and electric rockets. And in electric rockets, we have arc jet and ion rockets. So with this review of classification, we go we will proceed to see each one of these engines in the coming slides. So first of all, let's see what's the difference between the propeller and the jet propulsion. So you are seeing two different airplanes in here. I got these pictures from the jet engine book from Rolls-Royce. Here you can see the cover of the book. You can have this book also, and you can look at it. So there is a mechanism of providing thrust force on both airplanes, as you know. One is by propeller, and another one is by a jet engine inside this nacelle. Actually, there is an engine, and it is a jet engine. So let's look at the propeller one. The air comes and hits the propeller, and then the propeller guides the air like this. So it moves actually a large mass, a large amount of air, but at a very low velocity. But what you have learned from your dynamics or from the fluid mechanics courses, it actually depends on the not only on the mass or on the velocity, but it depends on both of them. That's what we call the change of momentum of air. So actually the change of momentum, which is the mass flow rate times the velocity of the air, will still be some value that will generate the thrust force for us in propeller engines. But in the jet engines, we actually have a small mass of air, but as you see, the arrows representing the uh, exhaust jet at the back of the engine are very bigger than the arrows that you see in the propeller engine. So the velocity will actually playing a major role in here, the difference between the inlet and outlet velocity. So again, the multiplication of the mass flow rate, here in the case of jet engine, a small mass flow rate, and the high velocity difference will generate the thrust force for us. So this is the main difference between the propeller and jet propulsion. So if you look at if you want to compare the piston engine and the turbine engine, we actually said that we do have a piston engines that we connect the propeller to these piston engines, and we use it in some airplanes. And in major airplanes, we do have the turbo engines or jet engines. We can actually have this uh, comparison table. As you know, the piston engines are intermittent engines. So we have those four steps of compression, uh, ignition, and the work, and then exhaust inside the piston engine. But actually, these are not actually intermittent in turbo engines, so it is continuously working, the turbine engine. Although we are modeling the cycle as a four-step cycle in turbine engines as well, but the way the turbine engine works is continuous. On the other hand, the piston prop engines, because it's been quite a while that we do have these engines, they are much cheaper than the turbo engines, and their fuel consumption is very low. But when you compare it with the turbo engines, their fuel consumption is very, very high. Although because of the material that is being used in the piston engines, they are very heavy, and compared to the lightweight of turbo engines. The noise also plays an important role in the uh, in this comparison because of the noise, the great noise and vibration of the piston engines, and the turbo engines are much quieter. So as we said, the piston engines are quite old and they are limited to some light airplanes and also some agricultural aircrafts. But the usage of the turbine engines or turbo engines is very wide in different applications, both military applications and civil applications.